Okay, so today we're talking about logarithmic and exponential models, and in the process of doing so, we'll visit also section 6.6, which is about logarithmic and exponential equations. So we're covering two sections here. 6.6 is due next Monday, but 6.7 is not due until after the Thanksgiving break, so that's not until the Monday when you come back. But there's only like 5 questions there, so there's not a whole lot in terms of 6.7. But we'll use it sort of as a motivating factor for studying this stuff in 6.6. So 6.6 is going to be all about solving these equations that come up, logarithmic the logarithmic and exponential sort of equations section 6.6 has a lot more work in it, but a lot of the reason or rationale for it is sort of to motivate solving these questions in 6.7. Okay, so that's what we're covering, and that's the last stuff. And then the remainder of the semester will all be basically reviewing for the final. So next Monday, as we sort of answer questions about the course and the Infinity homework, we'll also discuss some stuff about the final exam. Okay. So the learning objectives for today are just twofold. The first is basically what's going on in section 6.6, and it's solving exponential and logarithmic equations. And what that means is just an equation that has an exponential in it, where the unknown is up in the exponent, or an equation that has a logarithm in it, and the unknown is on the inside of the parentheses of sort of some logarithm. And then we'll also talk about how to solve some applied problems, and one of them is actually a question from the sample final exam. So we'll get you a final exam that you can use to study for the real final exam, and one of the questions we'll see today is from that. Okay, so that's really all we're after, and we're going to really sort of talk about number 2 first, and then we'll get into all the details of, you know, the different types of equations that can show up and the different methods that you'll want to use. And what we'll need is just a quick reminder of some of the properties of logarithms that we've been looking at. And let me just remind you of the product rule, the quotient rule, and the power rule. And that's just saying the following: the log base b of x times y is the log base b of x plus the log base b of y. So we were calling that the product rule. And then we also had the quotient rule. So the log base b of x divided by y just became subtraction, log base b of x minus log base b of y. And then we had probably what's going to be the most important rule for today, the power rule. So if we take log base b, and this is again any base b, right? So any positive number that's not equal to 1. If you take x to the power of y, well, then you can take this y from the exponent and move it down to the front, and you take it as y times the log base b of x. And this one is going to be sort of the most important one because it allows us to take an unknown from the exponent and bring it down to the front of the logarithm. And so we'll be able to use that to solve a lot of exponential equations, so equations that have an unknown up in the exponential. Okay, and then we'll also be able to use these pieces to solve logarithmic equations by basically taking the equation and condensing down the logarithmic expressions as much as possible, and then inverting them with an exponential. So we'll talk about that as well. Okay, so here is a good example of an application, and you'll end up having to do a problem eventually in 6.7 along these lines, and there's something I think also in the sample exam related to this setup here. So let me just give you a moment to read through this, and then once I've given you a moment to read through it, we will talk about some of the steps and the equation that you need. Okay, so as you guys read that, I'm going to put up on the board an equation that we'll need to solve this. Okay, so hopefully I've given you enough time to at least read through this, and those of you that are copying it down to maybe write it down. But let's now go through this sort of on our own and imagine sort of what's going on here, right? So this is the sort of question you'll get in 6.7. And we're going to use it to set up some exponential equations, and then we'll solve those exponential equations like we would in section 6.6. Okay, so let's say Thanksgiving is coming up here, so let's say you make some cheesecake and you take it out of the oven, and the internal temperature is 165 degrees Fahrenheit, right? So you've been cooking this cheesecake and you take it out. And you have a refrigerator and you'd like to cool the cheesecake off, so you place it right into your refrigerator, and the refrigerator now is set to 35 degrees Fahrenheit. And what happens is the cheesecake begins to cool off, okay? And you check after 10 minutes. You're excited about your cheesecake here, and so after 10 minutes, you sort of check the temperature, and unfortunately, it's only 150 degrees, right? So it still has quite a bit of time to cool off before it's going to get down to something closer to 35 degrees. And the question that we'd like to answer here is the following: how long will it take for the cheesecake to cool off to a temperature of 70 degrees, right? So maybe this is like the ideal edible temperature here, right? 70 degrees or something like this. And the question is, like, how long is that going to take us? Okay. Are there any questions about, sort of what's going on here? Does anybody need a clarification? If you're okay with what's going on, just give me a thumbs up, and we'll then talk about the equation that you're seeing in front of you and where that comes from. Okay. Right, so we've made cheesecake, we put it in a refrigerator, and it's cooling off. One of the beautiful sort of facts about nature that was discovered by Isaac Newton, the guy who discovered sort of the equations for gravity and the three fundamental laws of physics, also discovered that when things cool off, they cool off in an exponential fashion. And the equation that you're seeing here is what's called Newton's law of cooling. And it basically is an excellent model for sort of how anything cools off. For example, a cup of coffee, right? So if coffee is cooling off, you can use this equation to determine the temperature as a function of time. And it really only depends on sort of three different parameters. The first two parameters are sort of the temperature of the surrounding space that you're in. That would be T sub S, okay? And then also the initial temperature, right? So like when you took that cheesecake out of the oven, or when you poured out that cup of coffee, how much temperature, what was the initial temperature at the start, right? And you'll decrease by an exponential factor, and the rate of decrease is determined by this value k. And that value k just depends on, is it a liquid, or is it cheesecake, or a turkey, or something like this. This will be negative because it's a decrease. It's the law of cooling, but we'll want to know what that value of k is, right? And so again, it just depends on whatever is cooling off. And this was discovered experimentally by Isaac Newton himself, right? So like doing experiments and keeping track of temperatures and that sort of thing. And it's called Newton's law of cooling. Okay, so let's use this law now to answer the question, right? Okay, so let me just on the side over here ask you a few questions, and you guys can respond in the chat. What, in this case, is T sub S? What's the surrounding temperature for this one? Okay. Yeah, it's 35 degrees because we place it into the refrigerator. Okay. So that's the surrounding temperature, and that's what we'll take for that parameter T sub S. What about T sub 0? What's the initial temperature in this problem? 165? Yeah, because that's the temperature of the cheesecake when we took it out of the oven, right? So that's the initial temperature, and this equation is keeping track of the temperature of the cheesecake as a function of time. So when T is 0, this is 165 degrees, right? So that's what we mean by initial. And what we'll need to do is use that information to solve for K. All right? So let's go ahead and plug that in. And we'll see the function that is now an exponential function. So T0 is 165, and the outside temperature was 35. And here, what we want to do is first realize that if we plug in 0, we're going to get 165, right? So let's just see that really quickly. If I plugged in T with 0, here I would get e to the 0 regardless of what k is. E to the 0 is just 1. And so this would be 35 plus 165 minus 35. The minus 35 and 35 would cancel. And indeed, the temperature when we plug in 0 would come back as 165. So in order to figure out k, we need to also use some other information in the problem. Sometimes they'll tell you what k is. They'll just like say this is the constant for k. Other times they'll tell you a little bit of information, like for example here, that you checked after 10 minutes and saw that the temperature was now 150 degrees. Okay, so what that means is that T at 10 is 150 degrees. Okay, and you can use that information now in order to solve for this value of k, because in this case you'll plug in 10 for t. So let me give you a few moments to try and write that out and simplify the resulting equations as much as you can, and from there we'll go through and talk about how you solve for k. And what we're doing is setting up the type of problem that you'll see in section 6.6, right? So at some point we're going to get to an equation that we would like to solve, and in 6.6 they'll just state what the equation is. They won't give you a word problem like you're seeing here. Okay, but try to write it out on your own, right? How do you put this information into here and get an equation where the only unknown now is k? Okay, so the value of the temperature at 10 is 150 degrees. And so everywhere over here, we're going to replace the T with 10. So this should be 35 is equal to, or I'm sorry, plus 165 minus 35 times e to the k times 10. Okay, so that's how you take this and you translate it into an equation where the only unknown is k. So now what we want to do is solve for k. Okay. And for some of the questions that you'll have in Infinity, they'll ask you to maybe solve for k first and then do the next step that we're going to do here in a moment afterwards. But let's go through and figure out what we want to do here, right? So we're after solving this equation up here. Let me erase the function and these parameters and focus just on this value of k. Now, the reason why this is an exponential equation, right, is that the unknown that we have is up here in the exponent. And anytime that the unknown is up in the exponent, you're going to have to use some sort of logarithm in order to extract that unknown from the exponent. Okay, and we'll use the power rule to do that. So what you want to do is try to isolate the term that has the unknown on its own, like if you were solving for just this piece of the equation. So with that said, what should my first step be? What should I add or subtract or divide by on my first step if I'm trying to isolate that e to the k times 10? Yeah, we should subtract 35 from both sides. If I subtract 35 from here, what do I get to? Yeah, 115. So subtracting 35 from both sides to get 115. What is 165 minus 135? I mean, that's just a number, right? Like it was in the equation here. So yeah, we're going to get 130 for this side. And then this I'm going to write as e to the 10k, because usually you write the number first and then the unknown second, right? Doesn't matter how you multiply things, but that's a little more standard. Okay, and again, we're trying to isolate this guy on its own. So what should we do now? Yeah, divide by the coefficient here, the 130. So that gives us 115 over 130 is equal to e to the 10k. Okay, again, we've just isolated this guy on its own. And there are two ways to proceed now. We can first think of maybe trying to take the natural log of both sides if we would like, and then undoing this e with the natural log to get just 10k. Or if you're more comfortable with the definition of the logarithm, you could just rewrite this in logarithmic form, right? In logarithmic form, this is ln, because that's the log base e, of 115 over 130 is equal to 10k. So we kind of thought about it again as taking the natural log of both sides. The natural log and the e cancel out to give you 10k, and then you get the natural log on this side. Or just using the definition. Okay, and now my final step. How do I get k on its own? What's my last step that I'm going to do to get that on its own? Because remember, we were after solving for k. Yeah, divide by the 10. So we get natural log of 115 over 130, all divided by 10, is equal to k. And at this point, it's probably best to maybe plug this into a calculator, because if you tried to type all of this into Infinity, it's just going to get sort of cumbersome at a point. So here, if you plug that in, you get negative 0.01226, right? And I'm just keeping a few decimals, right? So this thing is negative 0.01226. And there were more decimals, but I just sort of stopped right there at the 6. Okay, so that tells me what my value of k is. And that's going to give us enough information to answer our final question, right? So let me just go back and remind you what we're trying to do. We've now used this info that after 10 minutes, it was 150 degrees. And now we're after answering this. If we must wait until the cheesecake is cooled to 70 degrees before we eat it, how long are we going to have to wait? So let's set up an equation that we could use to figure that out. And hopefully you'll see why we needed the k, right? So I'm just going to erase, let me put this back up for a second, so in case anybody wants to write it down. But I'm going to erase this here in a moment. So if you have it written down, how we found k, let me have a thumbs up and then we'll move on to the next piece here. Okay. I'm going to erase this part at least. Just coming back to this equation, this is what happened when t was 10. We didn't know what the k was at this point, but we knew it was 150 degrees. In the new setup, we have to make sure that it's 70 degrees, right? We're interested in when is the cheesecake going to be 70 degrees. So when is the temperature 70? The surrounding temperature is still 35 degrees because we're in the fridge. 165 is still the initial temperature that we took the cheesecake out at. We now know the cooling factor, the K value, that's going to be negative 0.01226. But at this point, we don't know what value of T gives us 70. So that's now the new unknown, right? So that's why we had to find K before, because if we would have just written this down, we wouldn't have known what K was, and there would be two unknowns in this equation. We wouldn't be able to solve for one of them. Okay, so we do the same thing that we did before. And again, this is just some good practice for the type of thing you'll see in 6.6. So I'll go through it quickly here. You subtract 35 from both sides. And then again, remember 165 minus 35 is 130. Okay, so I just subtracted this 35 here, and then 165 minus that 35 there. We'll divide by the 130 again. And then we'll convert it over to logarithmic form. So this is the natural log of 35 over 130 is equal to negative 0.01226 times t. And your final step is to isolate t on its own, so you'll divide this side by 0.01226, the negative of that. And so if you do it to that side, you've got to also do it to this side as well. And over here they cancel out, and you're left with just t. And on this side you have something you can type into a calculator, okay? And in this case, when you do, you get 107.027. Okay. And in this case, that's going to be minutes. So what did we need to plug into here in order to get an output at 70? Well, it was 107 minutes. And if you're wondering in terms of hours, that's 1 hour and 47 minutes. So almost about 2 hours. Okay, so we now have the answer to our question, right? Based on Newton's law of cooling, we're going to have to wait about 2 hours when we take that cheesecake out into the oven in order to eat it at 70 degrees. Okay, and the point here is just to show you where these exponential equations and logarithmic equations are coming from. They're coming from questions sort of like this, and there are other applications as well that you'll see in 6-7. But we'll focus here in a moment on just solving them, right? So for now, we saw how to set them up and where they come from. Let's see one more example, and this is from the sample exam, the sample final exam. So something like this could show up potentially on a final exam, and certainly on the sample exam. So let's go through and talk about this one. Here we have to remember what our formula was for compounding interest in a continuous way, and that's where we sort of defined the idea of the exponential e, right, Euler's constant. So in the case that you're looking at continuously compounded interest, its P of t is equal to P, which was the initial principal, right? The amount of money you either borrowed or lended out. And then it was an E, that was the Euler's constant E to the power of R times T. And again, the E came from just, increasing the number of times we compounded to larger and larger numbers, right? So we would compound twice a year, or 3 times a year, 4 times a year, every second, every minute, and more and more and more, right? And we got to this, right? This is what we called the continuously compounding interest formula, PE/RT. And there was also a formula for when we compounded n times, but here this is for the continuous. And what they're telling us is how much money was deposited in the account initially. So 6,500, that's your P. And they're telling us what the annual interest rate is. They're telling us what the R is. So in this case, the annual interest rate is 7.2%. But that's not, we shouldn't write 7.2 for R. That would be far too big. What number should we use for R in this case? Okay, yeah, so we just moved the decimal over 2 places, and if we move it 2 places to the left, we get 0.72. 0.072. I said the point in the wrong spot there, but what Blake said here is correct. Okay, so again, we just moved the decimal over 1, 2, and we have this guy. That tells us our value of R, right? And the question is, what's the value of T so that the output here is now $7,000, right? So when does this investment or this account grow to $7,000? And you can just set up the equation like this. So it's, when is this equal to 7,000? Well, the initial principal was 6,500. And this is then E to the 0.072 times T. And you can see that we have an equation here, an exponential equation, where the only unknown is T. And it's up in the exponent, right? It's up in the exponent. So we'll need logarithms in order to solve it, right? That's the only way we're going to be able to get to those exponents up in the, or those unknowns up in the exponent. Okay, again, we try to solve for the piece that contains the unknown. So what should we do first? What's my next step here for this problem? Well, yeah, so we don't want to subtract because it's not adding together here. If it was addition, then we would subtract this guy off. But it's multiplication, so we got to divide, right? Okay, so go ahead and divide by the 6,500, and we get 7,000 over 6,500 is equal to E to the 0.072 T. Okay, and then from there, you just convert this over to a logarithmic form, right? I mean, or you can think about it as taking the natural log of both sides. So you get ln of 7,000 over 6,500 is equal to 0.072 times T. And then the last step here to solve for this T, so let me move up here now, to solve for that T on its own, you just divide both sides of the equation by this 0.072, right, that interest rate. So here you get the natural log of 7,000 divided by 6,500, and then all of it divided by that interest rate of 0.072. And when you type that into a calculator, you get 1.0293. And that's years. And so it's not very long, right? I mean, about a year later, your money has grown by $500 from $6,500 to $7,000, provided that you're making, interest of 7.2% annually. And that's even when you compound infinitely many times, right? So even though it sounds sort of a bit suspicious where you're compounding so many times, the output here is not unreasonable. $500 over about a year. Okay, so again here, let me just come back to the question so we can see how long will it take us to get to $7,000? Well, this is just telling us that if we take that 1.0293 and we plug it into our formula here, then we're going to get an output of $7,000. So the answer here is about 1 year, right? 1.0293 years. Okay, so I think that's enough for setting up these equations. Sort of. You could generate more interest by increasing the interest rate. So instead of 7.2%, you could have 8% or something like that. But the number of times that you compound can't be increased anymore, right? And if you were to have compounded, say, 5 times or 4 times instead of continuously like you are here, then certainly it would take longer in order to get to 7,000. Okay, so again, this is 21 off of the upcoming sample final exam. Okay, so now that you've seen sort of why you might be interested in exponential equations and logarithmic ones, let me just go through some of the things you see in 6.6. So in 6.6, they don't justify sort of like any models or anything like that. They just give you an exponential equation and say, okay, go through and solve this guy. And again, we know it's an exponential equation when the unknown, the thing you're trying to solve for, is up in the exponent. So notice here that the x, that 3x, is up there in the exponent. So we've got to really go through and use some sort of logarithm at some point. This one says to use like bases. And the idea here is you could express everything base 2 and solve the problem that way. But I'm going to avoid doing that. And I don't think it's not part of one of our learning objectives. I think it's in the exam as a learning objective, or in the textbook as a learning objective. But here, I don't care too much if you write this as a like base. Instead, I'll just use the same base over and over. I'll use the natural logarithm. So like I said before, you don't really need to convert things over to their logarithmic form if you're just using one base, and I'll use ln for everything that we're going to do. Okay, so the way that we'll solve this problem here is, again, to first isolate the term that has the unknown, right? Or the factor that has the unknown in this case. So that is the 1/4, the 1/4 to the power of 3x. So to get that on its own, what do we need to do to both sides of the equation? So again, we're trying to get the 1/4 to the 3x here on its own. Yeah, so that's right. We just want to divide by the 8. And let's just say we don't even know what 2 to the 7 is yet. Like, we haven't typed it into a calculator or tried to compute it yet. All we're doing is writing it as 1/4 to the power of 3x is equal to 2 to the 7th divided by 8. And again, all I'm trying to do is isolate this thing like if I were isolating the x on its own. Okay, so now you could try to write this in base 1/4 or base 2, but that would sort of be a pain. And that's not 27, that's 2 to the 7. Okay, 2 to the power of 7. But I'll just take the natural log of both sides, right? So here, I'm going to take the natural log of this side. And if I take the natural log of that side, for everything to be equal, I have to take the natural log of that. This is just a number, so this is something I can compute, right? Over here, we have the unknown, and here's where we'll just sort of leverage the power rule. This 3x, because of the power rule, can be just brought to the front of the equation. So that 3x comes down to the front, and then we have that natural log of what's left over is the base, 1/4, and that's equal to the natural log of this number here, which is 2 to the 7th over 8. And natural log of 1/4 is a number as well. So we can divide both sides of this equation by this natural log of 1/4, and it'll cancel out on this side. Okay, and then we can also divide by a 3 on this side, and if we do it on this side, we've got to do it on that side as well. And what's left over is just the x. Okay, so here we've got x is equal to the natural log of 2 to the 7 over 8 divided by 3 times the natural log of 1/4. This is a terrible way to write the answer, but it's still the answer, right? Like you could plug this stuff right into a calculator and get out a decimal answer. You'd get negative 0.66666, but and then it would just continue on with a bunch of sixes. But if you typed it into infinity, because infinity is the calculator itself, it would give you the right answer, right? And this is it. This is the number. But let's go through and just sort of see how we could simplify this a little bit, so we can see why it's actually equal to negative 2/3, which is the fraction form of 0.66666 continuing infinitely with infinitely many sixes. Okay, so let's just say box that as our answer, but now let's go on to a little bit more and find the exact answer here. And one thing I'll point out is that 8 is 2 to the power of 3. Okay? So really, we've got something like this. The natural log of 2 to the 7 over 2 to the 3 divided by 3 times the natural log of 1 over 2 squared. Because that 4 is 2 squared. Okay, so now let me just rewrite this a little bit more. 2 to the 7th over 2 to the 3 is going to be the natural log of 2 to the power of, not 5, but what? 2 to the power of what? Yeah, so remember this is 3 down here, and we do 7 minus 3, so we get a 4. And then down here on the bottom, I'm going to write this as 3 times the natural log of 2 to the negative 2. Now, in terms of infinity, you could have just typed in this answer down here and hit submit, and you'd get the correct answer, right? But I'm just trying to show you where the fraction comes from, because in some of the questions, they simplify things down quite a bit more. Okay, so what happens now, we can pull the 4 down to the front here. This becomes 4 times the natural log of 2. And then we can pull the negative 2 down to the front here, but there's already a 3. So negative 2 times 3 is going to give us negative 6. And then notice there's a natural log of 2 here and here. Right, those cancel out now. And you're left with negative 4 6, which is negative 2/3. So if you typed in negative 2/3 into infinity as well, you get the right answer as well, right? Okay, so this guy should have been fine, but it's also equal to negative 2/3, the point here. So I'll just circle this one because this is completely simplified. All right. Let's continue on. So here's another interesting one. And the point of this example here is just to show you that not everything will have a solution, right? So there's going to be a few questions on 6-6 that if you tried to solve them, you would get something that was not a solution. This is an example of one. So here you would try to isolate that r to the 14, or e to the r plus 14 on its own by adding 14 to both sides. So you get e to the r plus 14 is equal to what? What should I put on the right-hand side here if I've added 14 to both sides? So again, here I'm just adding 14 to, yeah, so 14 plus negative 32 is negative 18. And if you already see the problem, you can stop the sort of the supporting work here and just say this is not possible. But if you didn't see that, you would want to take the natural log of both sides. So here you would get the natural log of e to the r plus 14, and over here you get the natural log of negative 18. And then you want to try and pull the r to the, e to the r plus 14 down to the front. But before you do that, if you type this into a calculator, you would get an error. And the reason why you get an error here is this is not in the domain of the logarithmic function, right? You cannot plug a negative number into a logarithmic function. And because this isn't in the domain, there's just no solution. And that should make some sense. There's no way you can take e and raise it to any power and get something that's negative. The graph is always above the x-axis, okay? So be a bit careful when you're trying out these questions. In some instances, there is no solution. And this is a quick example of that sort of thing. Okay. Here is another example, but I think we're running a little bit late on time, and this one's sort of close enough to the last one that it's, I think, better for us to go on. But I'll just mention, in this case, you don't get a negative on this side of the equation when you solve for that 2 to the p plus 9. You get something that's positive. And so you can actually go through and then just solve for p. Okay, but here's something that shows up that's a little more difficult, and it's going to require you to use a little bit of factoring. It's probably one of the tougher ones in section 6.6, so I should give you a little bit of insight in how to solve this sort of thing. So it turns out this is a quadratic, and it's e to the 4x squared for that first term, right? E to the 8x is e to the 4x squared, and then this is minus 5 times e to the 4x, and then minus 24. And so it turns out you can factor this thing and set the factors equal to 0. So here, this would be an e to the 4x, and this would also be an e to the 4x. One of these would be positive, and one of them would be negative, because this is a negative 24. And so this would be e to the 4x, e to the 4x, so that's why you get e to the 4x squared. We need two factors that multiply together to give us 24 and add together to give us 5. What do we get for those two factors? Two things that multiply together to give us 24, but add together to give us yeah, it's 8 and 3, right? Which is the negative? Well, we'll notice here that this is negative 5, right? So the larger, yeah, it should be negative 8 here, and then positive 3. So 3 plus negative 8 is negative 5, and 3 times negative 8 is negative 24. Okay. So the same way we would normally factor, except there's exponentials here. And from here, we'll set those two factors equal to 0, just like we would for a regular old quadratic. So this is e to the 4x plus 3 is equal to 0, or e to the 4x minus 8 is equal to 0. And this one over here, we move it to the other side, and we get e to the 4x is equal to negative 3. And so we can see this is a no solution one, right? Because it's not possible for e to the 4x to ever be negative. We could have taken the natural log of both sides and got an error, but there, that one's going to lead to nothing. This one's going to lead us to e to the 4x is equal to 8. And I'll move that one up here to the top because that's going to give us a solution. You take the natural log of both sides, or just rewrite it in logarithmic form, and you get the natural log of 8 is equal to 4x, right? The e and the natural log cancel each other out, so you're left with just 4x. To get the x on its own, you divide by 4. So natural log of 8 over 4 is equal to x. And again, this is something you could type right into Edfinity for your answer. Okay, so a pretty tough one here, where you've got to do sort of two things here, exponential and quadratic. Probably one of the tougher ones that you'll see in 6.6. Okay, so now let me end with two last examples. And mention that everything we've seen so far are exponential equations, right? So the unknown is up in the exponent, and that's what we call an exponential equation. But this section also had what are called logarithmic equations. And a logarithmic equation is something like this, where the unknown is inside of a logarithm. And anytime the unknown is inside of a logarithm, you have to be careful because there could be extraneous solutions. You may get, as you solve this thing, some solutions that are not really solutions. You always have to check your answer at the end, just like you do for square root equations and things that have radicals. And in these instances, what you want to be doing is the process of condensing the expressions on the left and the right-hand side. So anytime that you're trying to solve a logarithmic equation like this one, your first step is to take the right and left-hand sides of the equation and condense them down as much as you possibly can. And what that means is using the product rule and the quotient rule in reverse, okay? So here we can use one of those two. Are we going to use the quotient rule or the product rule? Which of the two rules should we apply first here? If we're going to condense, one side is already condensed. The natural log of 47 is condensed as much as it possibly can. But if it wasn't, we'd have to also do the same thing to the other side. Yeah, we're going to use the quotient rule here because of the negative sign, right? So the quotient rule tells us that subtraction was coming from division, right? So the natural log of a division. And so we'll combine these two things together into a single logarithm here. It'll be the natural log of a quotient. And it's the x plus 10 over x. And the whole thing is equal to the natural log of 47. Okay, so you'll notice I condensed everything down to a single natural log on this side, and I condensed everything over here. It was already in that format to a single natural log there. And we'll use the fact that e undoes the natural log, right? So the exponential function is the inverse, and so we'll take e to this side, and that'll be equal to e to that side, right? The e and the natural log will cancel out, and you're left with just x plus 10 over x is equal to 47. Okay, so we want to isolate x on its own now. You'll notice this is no longer a logarithmic equation, and that's the goal, is eventually you condense everything down, you use e on both sides or whatever the appropriate base is to undo the logarithm, and you get something that no longer has any logarithms in it. Okay, so here you'll move the x to the other side. X plus 10 is equal to 47x. And then you want to get the x on its own. So we'll subtract this x to the other side, and we get 10 is equal to 46x. And then divide by x. Or, I'm sorry, divide by 46. You get 10 over 46 is equal to x. And that's the same thing as 5 over 23, if you're simplifying it. Okay, and then in the last 2 minutes here, I'm sorry for moving so quickly here. We probably should have went through those first ones a little faster. Here's another example. This one, instead of using the quotient rule, uses the product rule, and that's because of this, okay? But here we have to also be careful because sometimes when we apply these rules, we introduce solutions that are not really solutions to the original equation. So one should always go back, and if you check the previous one, you would find that it was correct, but you should always go back and check your work. Okay, so here, in this case, the left-hand side is the product rule, so it'll be rewritten like this. So now we've got the natural log of x times x minus 3 is equal to the natural log of 7x. Okay. And then let's just go ahead and undo the natural logs. So I've compressed everything down. I take e of this side and e of that side. And we're left with x times x minus 3 is equal to 7x. Okay, so this is a quadratic. We should move everything to one side of the equation, but let's distribute first. So x squared minus 3x is equal to 7x. You subtract the 7x from both sides of the equation. X squared minus 10x is equal to 0. And now we've moved everything to one side of this equation, right? And again, the goal was to get rid of the logarithms. So now we're on to this quadratic. Here we'll just factor it. The factors are x and x minus 10. because the greatest common factor here was just x. And then you can go through and set those factors equal to 0. So this is x equals 0, and x minus 10 is equal to 0. So here we get x is equal to 10 for this last one. And before we box our answers, we should go back and check that these are indeed solutions. So in the last sort of minute here, let me just mention why the first one is not. Notice here that we have the natural log of x in this question. And if I plugged in 0 there, it's not in the domain. So that natural log of x, where x is 0, is undefined. So this is not one of the solutions. This is an extraneous solution. On the other hand, if I plug in the 10 and check the left and the right-hand side, when you plug it in and plug it into your calculator, you do indeed get something that is a solution. So x equals 10 is the only solution in this case. So again, this is a good example of you have to go back and check your work. So logarithmic equations, condense as much as you can on both sides of the equation, undo the logarithm, and then hopefully you end up in something simpler. Okay, and that's it for today's lecture. So thanks for being here, guys.